Hey, welcome to Polynomials. This is part one, just the basics. And let's have a look at the name, Polynomials. And when I saw that, I thought, hey, I've seen a few other words with poly in them. Polymer in chemistry, or in organic chemistry in particular. Polygamy, more than one partner. Polymer means what? More than one molecule, repeating molecule to form a polymer, or many somethings. Polygon, many-sided figure, hexagon, octagon, different numbers of sides, and polydextrose. Oh, that's an artificial form of glucose there. And what do you think they all mean? Poly is usually meaning many from the Latin. So many. So what's a polynomial? Many numbers, many terms is what we would say. So what we're going to study now is something that you've already started. You've done expressions before with many terms in them. It could be a linear expression, 3x plus 2, or it could be something like here, one more term, three terms, three different terms there, 4x squared, 3x, and negative 7. And that's a quadratic, isn't it? I think you've already seen that. And we call the highest powered term, we put it in the front, highest power, then 1 next power, and so on, as they decrease. And that first term is called the leading term. And then the term with the variable to the naught, I suppose, x to the naught is 1. So negative 7 could be thought of as negative 7x to the naught. That smallest power in a polynomial is called constant, of course, because it doesn't have a power of the variable other than naught, which produces 1. Okay, and then, of course, we could build them. Can you see how big this area of polynomials might be? This is now called a cubic. Quadratic, a cubic. Why? Because the highest powered term here is a 3, or a cube of the variable, and then 1 less power, and so on. I think you're starting to see some properties. We'll come down here in a minute and summarise them. And if you were to draw the graphs of these high-powered polynomials, of course they get to be a bit fancy. Here's what's called a quartic. Really should have here y equals x to the fourth, take 2x squared. Hey, the cube's missing, mate. And also there's no constant. So we're going to have to watch that in setting up our structure of our polynomials here. See what powers are present and what are missing. And drawing graphs. This looks interesting stuff. What about this as our definition down the bottom here of a polynomial? We've got varying coefficients. And so here we would say an is the coefficient of the term x to the n, where the variable name is x raised to the power n. And then a squared is the coefficient of the x squared term. Can you see something interesting that we can see from this page introducing polynomials? And that is that the powers n is a member of j plus, or the integers, positive integers. Okay, so we don't have things like x to the neg 1 or x to the neg 2, and we don't have, so they are out, and we don't have things like rational powers, x to the half. So the typical polynomial is of this form, where the powers of the variable are positive whole numbers. So keep that in mind now, and you of course got a constant down the end, which has x to the naught, or no x term at all, saying x to the naught would be 1 for the as long as x is itself not equal to naught. All right, so you've got an idea. It's going to be a huge family, isn't it? The family of polynomials. Let's go down and have a look at some of the things that are going to come about as we look at this area of maths. So there we have it. We can have a linear one, quadratic one, cubic, and quartic, depending on whether you think of polynomials as polynomial many powers or polynomial as many terms. So the linear joins in there if it's many terms, because it's got 2 terms. If you thought about it as many powers, it's only got 1 power of the variable, although you could think of it as x to the naught, bx to the naught. So anyway, we start the polynomials with the linear function, and the quadratic is really the great gateway to the other interesting ones, for reasons you've already seen, but you might have forgotten. And so here we are. We're going to be, in this course, talking about real polynomials only. So in other words, the coefficients of the various powers of the variable are themselves real numbers. They don't contain I. Okay, where you can't have a complex coefficient. So what's not in this group are things like this. Okay, that's a possible a polynomial because it's got positive whole powers of the variable there. That's a possible polynomial expression, but it's not included in this course because we don't include complex coefficients. We only have real coefficients, so we're going to be dealing with real polynomials. Okay, let's go down and start to build this area of mathematics up. And so that leads on, if we're saying we're only going to have real coefficients, it leads on to this link to what we did before with a little bit of complex numbers. Do you remember how complex roots can hide in a real polynomial equation? In other words, you've got real coefficients, yet you get complex roots. Because they are the sorts of things that we are interested in here, where we have a polynomial expression or an equation where the coefficients are all real. But does that exclude any connection with complex numbers? It doesn't, does it? Let's go down and answer that question. Here it is from before. If you've got a pair of complex conjugates, you can form a quadratic equation which has only real coefficients. So the answer is, if you've got a real quadratic equation, it doesn't preclude the presence in the background of complex roots. Because just remember, this is this coefficient of x. Let's get rid of that bit there. The coefficient of their x, this neg 2c, is real because it's minus the sum of the roots of the equation. We did this before, and the sum of the roots is c plus di plus c take di, and c plus c is 2c and the di's cancel out. So the sum of the roots minus the sum of the roots is neg 2c or minus 2c. And this is, remember in the structure of a quadratic equation, the constant is the product of the roots. Product of the roots. And we proved this in an earlier presentation. And the product of the roots here with a conjugate pair is c plus di by c take di, which is c squared take d squared I squared, or c squared plus d squared, as I squared is neg 1. Okay, so you can see here, therefore, that this quadratic equation actually does have real coefficients, but it's got complex roots there. And if they occur as conjugate pairs, they are hiding within those real coefficients. Okay, so keep that in mind, but we're talking about only real numbers here in our polynomials, but in the background there could be some complex roots to the equations. Okay, let's come down now and have a look at doing some operations with them. This is a bit of a review because in previous study you've probably done things like adding up many powered expressions here, or polynomials. So if you add them up, of course it is about adding and subtracting like terms. Okay, and this isn't a bad hint. Put brackets around the terms that you're adding or subtracting. So we're adding these two polynomials, so write it out. There's the first one, plus there's the second one. Not a problem there. Don't need a bracket for that one because there's no negative out the front. We'll collect up the cubes, x cubed plus 2x cubed, 3x cubed. So this is really a review of collecting like terms, more than it is a review of polynomial algebra. Neg 2x squared plus x squared is neg x squared. 3x, there's no 3x over here, so it stays just as 3x. Neg 5 take 11, neg 16. Do you get it? It's only collecting like terms. Now the bracket thing is important here. As we take this away, we want to take away every term, so we've got to remember to apply that subtraction to the whole bracketed term. So this becomes neg 2x squared, negative by a positive is a negative, negative by a negative is a positive. Okay, so when you go through all those, we've got x cubed, take 2x cubed is neg x cubed, neg 2x squared, take x squared, neg 3x squared, and 3x is just the only x term in the two expressions. Neg 5 plus 11 is positive 6. Do you get the idea? Okay, so I think you can do that. Nothing much new there. let's have a look at multiplying the expression by a scalar, or just a constant. It relates back to vectors as well, where some numbers or some expressions specify a magnitude and a direction. But here we're just talking about a scalar, and we're multiplying the whole expression, the whole many-term expression, polynomial, by the one number. So if the p of x is that and we want to multiply by 3, you're going to multiply the whole thing by 3, each term. So the use of the bracket is important to remind you. It's 3x to the fourth, 3 by neg 2x cubed, neg 2x cubed, neg 6x cubed, 3 by 4x, etc. Okay, so multiplying each of them. And then neg 2p times polynomial. Be careful, negative now, all terms within a bracket. Neg 2 by x to the fourth is negative times positive negative. Negative by negative is plus 4x cubed. Negative by plus 4x, neg 8x. Negative by plus 7, neg 14. So fairly simple ideas from work that we've done before. Let's have a look at polynomial multiplication. So what we're doing is we introduce an idea of a family of functions here, and we want to work with them and perform various operations with them. So here we're going to multiply two polynomials. We multiply every term of the first polynomial by every term of the second, and then collect like terms. This goes back to an understanding of FOIL, doesn't it? A plus B by C plus D is the sort of mummy or daddy of each of these. This implies in mathematics land we've got A lots of C plus D plus B lots of C plus D. That's what that notation means. So at the end of the day, you're going to do all these multiplications. Consequently, this sort of rule or algorithm appears. So here it is down here. This means I've got x cubed lots of this, there it is. Take 2x lots of this, there it is. And then plus 4 lots of this, there it is. So it's an expanded, what do we call this? FOIL, first outers, inners, last, and that sort of thing. It goes back to those junior maths days to remember how to do it and not leave out any terms. When we do, of course, it's just a matter of multiplying each of those brackets out and then, of course, collecting the terms. And you could put it down like this, but the easy way there, of course, is to line up like terms. So you can match them up. Not a bad little trick, or you can just put it all in a line, and when you have finished with it, rule out the particular terms. Anyway, so just check that. Fairly simple revision there, I think. All right, come down. I want you to do a little bit here to sort of warm up on polynomials. So here's a few polynomials, and the answers are down below. I think you should go through and just make sure you do all of these, because this is fundamental operations with our new family of functions here called polynomials. Okay, what's the negatives in here? That you do subtract this whole following function, and here make sure here f of x squared, two brackets, and just multiply each term by each other term. All right. So pause the presentation, have a go, and I would do have maybe question 1 and then check the answers as you go, so you're making sure you're not repeating an error, that what you're doing and what you're practicing is correct. Okay, so I'm going to go on with the answers now. So come down here and we'll have a look at the answers to that first set of questions now. So that's question 1, 2, a couple of parts of question 3. Going through and check carefully that you're getting the perfect answer here, because this is fairly fundamental to what we want to do later on in a more... this gets very interesting. It's a bit mechanical at the moment, but get your mechanics right. Your car's not going to run unless you've got good mechanics, mate. All right, come down to question 3. And we've got A through F there. Okay. All right, so check it off. Go back and make sure you can see what went wrong, if you got any wrong. Let's move on now and have a look at a little bit of extension here now. Division of polynomials when you're dividing two many-termed expressions. So first of all, let's have a look at an expression like this. And if we expand it, you'd have this cubic polynomial. Highest power is 3. Okay, so if we then divided that by x plus 2, then you could change the top line back to the factored form plus 7. And what happens? Well, when you divide it, you can cancel that into there, but you also have to divide the 7 by x plus 2. So what we would say is this division goes this many times with a remainder of 7, and that becomes 7 over x plus 2. That's a fraction that we've got left. Where do you get that from, mate? Let's come down and just review division a little bit. Here it is from junior maths stuff. 25 over 9. How many times does 9 go into 25? 2 9s are 18, and you've got 7 over. Do you remember, you say it goes twice and a remainder of 7. That's a quotient, remainder of 7. Or you could say the overall expression was 2 and 7 ninths. Right? Because 7 was not able to form another whole, it was 7 ninths of a whole. Okay, so please remember that basic short division algorithm, because that points us to what the real meaning of division of polynomials might be. First of all, have you got a question for Huddy? Does it make sense, hang on, I'll just do this differently, to divide two polynomials? What are we really saying there? Should that be possible? Okay, think about that. Okay, what do you think? Well, yeah, polynomials are expressions in a variable where the variable x can take various numbers. So they do actually only represent in the long run numbers, don't they? At particular, if you evaluated them at particular values of the variable, they do represent numbers divided by numbers. So it is okay to try and do it in x land, because x is just standing for a number. Okay, and you see here, they have the common variable, so when x takes a particular value in the top line, it will take the same value in the bottom line, and it will just end up one number divided by another. So it is a sensible thing to be talking about, division of polynomials. I wonder if you thought about that. All right, so come down and let's have a look at this. Now this is a little bit harder. Will we show the whole thing? I'll just bring this up a bit. Yep. Okay. Wow, what's going on here? And to understand this, I think we really do need to look at the long division algorithm. Let's say 359 divided by 22. What do we actually do? It might be a long time since you saw that. So 359. First of all, 22 into 3 doesn't go. Then we group these together. 22 into 35 goes once. 1 times 22 is 22. But what do we got left? Take it away. We've got 13. Then we go to the next units. Okay, we're down to just 9 units. 22 into 139. Well, I think it goes 6 times. 6 times 22 is 132. We take it away and we've got 7 over. Okay, so now 22 doesn't go into 7. So what's the answer? We say it's gone 16 times and 7 22nds left. A fraction is left. What we say here is the quotient, the number of times it actually goes, is 16, and the remainder is 7, or we can say 359 over 22 is 16 and 7 22nds. Now this idea here, this is driving the algorithm for division of polynomials. Algorithm meaning the method. Why? Because polynomials are just numbers at the end of the day when you substitute a value of the variable in. So it is relevant to try to emulate this or copycat it over here. So come over here now, and we've got this one we did before, divided by x plus 2. And we're pretending we don't know that x plus 2 is a factor now, so we can't cancel it. So let's do the process. First of all, what are we going to do? Well, we need to multiply x by something to get 2x cubed. What do you need? 2x squared. So 2x squared by x is 2x cubed. We take it away, and all the x cubes are gone. But hang on, if we're multiplying that by 2x, we've got to multiply that part of the number also by 2x. So it's 4x squared, sorry. 2x squared by 2 is 4x squared. So taking it away, 3x squared, bringing the 10x down. Can you see, in x land, it's the same as what we did over here. Come over here, bringing the next number down, and we're trying to duplicate that. And because we don't know the value of the number, we've got to work with x's. Okay, so now, how do we get, we've got 3, when you take it away, you get 3x squared, so we need 3x by that leading term, 3x squared. But you must multiply by 2, so you're generating, this is where it's a little bit different, you're generating 2 terms each time, and the first one, if we follow the algorithm, has got to go out, and then 10x takes 6x is 4x, bring down the 15, do it again. What do we multiply x by to get 4x is 4, and 4 by 2 is 8. Do you get the idea? Then that wipes out, no x's, and we've got 7 left. So what have we just shown? We've shown that the quotient, the number of times it actually goes, is that, and 7 is the remainder, so we've got 7x plus 2ths. Nothing to do with dentistry, mate. Anyway, so x plus 2 is called the divisor, the thing we're dividing by. This is called the quotient, the number of times the expression goes in completely, and r is called the remainder. So it's very, very important to be able to write the expression in that broken down form, and we're going to have a look at that now. So come down here and let's have a look at this form now. Alright, so if you've got a polynomial, right, many terms, and you're dividing by a linear factor, then this is the number of times it goes, because the polynomial up here could be what? Well, it could be linear, which in case it just goes a constant number of times with a remainder, or it could be a quadratic or a cubic. So when you've done a division, you've got a lesser degree polynomial here and a remainder. And you could keep dividing it until this doesn't go into this anymore. Like we did up there, we stopped when we had 7, because you can't multiply something with x a certain number of times to get just 7. So that was left as a remainder. Okay, so again, ax plus b is the divisor, q of x is the quotient, and r is the remainder. Okay, and it will depend on the degree. What degree or leading power, highest power, you have for p of x. Okay, now there are 2 alternatives. That's one way of writing what you've done. You've done the division, this is how many times it went, and this is the fraction. Or you could multiply both sides by ax plus b, and say, therefore, multiplying that by x plus b, you get p of x equals q of x times ax plus b, and cancelling here plus r, remainder. So there are 2 ways of representing that outcome. One is as a strict quotient, up here, dividing, and you get how many times it went and a remainder. The other one is saying, well, if you wanted to formulate an expression for the polynomial, it's this many lots of the divisor plus the remainder. Okay, so be flexible. Try to think of it in both ways, because both are useful in problem solving. Okay, come down here a bit and let's give you a go. So here we are. We have this cubic divided by a linear. So write it out, make sure all the terms are in order so you don't make a mistake. What do you multiply x by to get x cubed? Put it up here over the x squared. It's x squared. So we're going to do that multiplication. X squared by x is x cubed. X squared by neg 3 is neg 3x squared. Take it all away. Look at the bracket there. X cubed take x cubed, nothing left. Okay, neg x squared take neg is neg x squared plus 3x squared is positive 2x squared. Okay, we bring the next one down. Well, you do it again. What do you multiply x by? This time to get 2x squared. We want to wipe that out next. So you've got to multiply by 2x. 2x by x, 2x squared. 2x by neg 3, neg 6x, take it all away, look at the bracket. 2x squared by 2x squared, that's the idea, nothing left there. Neg 3x, neg by negative is positive, neg 3x plus 3x is 3x. Bring the 5 down. Can we go again? Yep, 3 times x is 3x. 3 times Neg 3 is neg 9. Take it away, they go out. Neg 5, watch it, take neg 9 is neg 5 plus 9 is 4. So we've just shown that when you divide these two, it goes that many times and then it ends up with this number, which is not divisible by an x take 3. It hasn't got an x in it up there. Or you can multiply everything by x take 3 and say, well, we recognise the original polynomial is this many lots of x take 3 plus 4. Just remembering what we're doing. We're multiplying that side by x take 3, this by x take 3, and this by x take 3, and so you end up with this alternative statement. So in the problems coming up, I want you to write the quotient and the remainder like this, and then the two forms, both of these forms, which explain the relationships between those. All right, study that and come down now, and I want you to do all of these. It's important to do all of them. Okay, it's because you need to practice this. This is an important idea now. Okay, explicitly mentioned in the specialist math syllabus. So pause the presentation, have a go, and as you do one, pop ahead and just check that it was okay. I'm going to show you the answers now. Okay, so there's question 1 with the working shown there. Have a good look at that. Go to question 2. Okay, down to C and D, E and F are a bit missing there. And then E and F. How'd you go? Okay, what's this sort of fraction work here? Bit hard when you start with the fractions. Okay, let's go on. Here's another one. Here's a little bit of a tricky do here. Notice this comment from the dude here. We've got some terms missing, no x cubed and no x. So we've got to be careful to line the terms up. This is why we put in naught x cubed and naught x, so we don't make an error in subtracting perhaps an x squared or an x term away from an x squared term. We've got to match it up so we're working with like terms. The notion is simple. You can only take away terms and add terms which are like each other. So here's our polynomial with the important zeros in there to space it out. Then we say, looking at the x, what do you multiply x by to get x to the 4? So we wipe it out. It's x cubed. X cubed by x is x to the 4th. X cubed by 3, 3x cubed. Take it away, they wipe out. And this is naught x cubed, take 3x cubed is neg 3x cubed. Bring it down like another number. What do you multiply? Again, x by to get neg 3x squared. Neg 3x cubed, we need neg 3x squared up there. Do it again. And now it's neg 9x squared. Take it all away. What's this? Negative times negative is a positive, so that's no x terms left. 2x squared, take neg, is plus 9x squared, is 11x squared. Bring no x's down. Keep it all organised. So now you need 11x to get 11x squared, and 11x times 3 is 33x. Take it all away, wipe out there. Naught x, take plus 33, neg 33x, bring the 1 down. Last number is neg 33, take 99. And you're going to subtract all that. 33x's go. Minus by minus, negative by negative is a positive, is plus 99. Neg 1 plus 99 is 98. Okay, so what have we just shown then? It went this many times, right? And 98 over 8, x plus 3. So this was the quotient. Didn't ask us for stating it there. That's the quotient. This is the remainder. And the other way of expressing what's happening is that polynomial, when it's that many lots of the divisor plus remainder. Always be prepared to think of it in two different ways, the relationship there. Okay, come down, and I think it's time for you to have a go. And of course these differ because you haven't got the other powers. There's no x in there, and there's no constant here. And in these here, well, that's okay, but there's no x squared term or constant on the end there. So just watch lining up the powers and collecting like terms accurately and appropriately. All right, have a go, but as you do one, I want you to check ahead to the answers to make sure that you're not getting it all wrong and then finding out right at the end. Okay, I'm going to show you the answers now. Okay, A, B, C, D, and pause it, check it, make sure you get all the signs right, and then come down now to E and F, and I hope you're having fun with these. All right, so we're getting some skills now. You're starting to work with many terms, polynomials, so that's good. Let's have a look at the last thing we want to do here. We'll just do this for a start and talk about degree of the result. So if you have a polynomial divided by a quadratic, now this is not linear, so we've got to try and do the process with many powers there. It'll go a certain number of times, then you'll have a remainder over a quotient. Notice that this could have x in it this time, because you're dividing by a quadratic. So once you get down to a power in the remainder less than 2, then it won't go again. So you could have a linear expression, one with x in it, as long as this e is not naught, or it could be a constant if e was naught. So the idea of, if you're divided by a quadratic, you could have a remainder which was a linear, because no further divisions are possible. I'll put this down. No further divisions once the expression has a degree less than the divisor degree. Okay, that's in the divisor's degree. So if you have a quadratic, once you get down to a linear remainder, it won't go anymore. You can't have negative powers. Okay, let's start to see that pattern. A little bit left here. I want you to complete the thing here with the same algorithm. This time we're dividing a quartic, highest power 4, degree 4, divided by a quadratic. Same process. Be careful now. What do you start with the leading term. What do you multiply x squared by to get x to the 4th? You need an x squared. But then you've got to multiply it by all of these. Neg x cubed and x squared. And bracket, take them all away. Nothing there. 4 take neg 4 plus is 5. Naught, because we didn't have, what's this? We didn't have an x squared term. So I had to put that in there. Take x squared is neg x squared, bring the next one down. So we're working in bundles of 3 here now, because the quadratic that we're dividing by, the divisor, is x squared, take x plus 1. Okay, so now, what do we multiply x squared by again to get 5x cubed? 5x by x squared, 5x cubed, and so on. Subtract it, and we end up with negative 2x take 3. Can we multiply over here x squared by anything to get neg 2x? No, not without using negative powers. And we're in polynomial land, and we do not have negative powers in polynomials. We don't have rational powers, or fractions rather. So how many times did it go? Well, here it is up here. It went x squared plus 5x plus 4 times, and the remainder this time did have x in it, because the divisor was a quadratic. Okay, so we can say our original function was this many lots of the divisor plus the remainder. Or they've only written it one way. I'd like to write it the other way as well. So let's do that. We have divided that expression out, and when we did, we found it went this many times, and the remainder was 2x take 3 over x squared take x plus 1. Always trying to write both summaries of what's happening there. Okay, are you ready? Can you do the big ones? Come down now and have a go at 3b2. And we're nearly at the end. I'll give you one alternative little process you might do and see what you think. So do these divisions, and I'd like you to put the answers here, not just in one form, both forms for what's going on there. Can you write the answer in both forms? All right, have a go and check your answers as you go. This is an important part of the syllabus, explicitly mentioned. I'm going to show you the answers now. Okay, so there's question 1, A, B and C. And question 2, A and B. We'll just go up and see if we can get E and F in. Yep, get E and F in. All right, let's go down and have a look at question 3. All right, now there's a little optional part of the syllabus here, and I think it's quite a good thing to be doing because later on in maths you might want to use this, and it's called synthetic division. So if we're dividing by a factor of the form x take k or x plus k, in other words, it's 1x plus k or 1x take k. So it's a rather special use of the division process. And here's the example. Then what we do is there's some rules. If you track through what we've done with the algorithm, what happens? Well, when you're dividing by x plus 2, you're going to take away the result at the end. So instead of putting take every time, we put a negative out here for the 2. So if this is plus, you put neg 2. See here, if it's x plus 2, we're going to subtract the term, so we often put neg 2 there, the opposite sign, so that you don't have to put subtraction each time. So, and here the coefficients, so we're just going to pluck out the important numbers. Now, we must have them in the right order, because they represent successive powers of the variable. So what we do is put a 0 under the first one, and bring that straight down. 2 plus 0. Then it's 2 times neg 2 is neg 4, and add them, and getting 3 here. Okay, so we're going to multiply those numbers and bring it down. All we're doing is identifying the pattern of the coefficients, and don't worry about the algorithm, just make it work, and we're adding them. Okay, so we're going to add these now because we've got the negative, the subtraction part of the problem, incorporated in the 2, if you like. Okay, so here we're going to add these, adding 7 and neg 4 is 3, multiply across, 3 by neg 2 is neg 6, adding is 4, multiplying across is neg 8, adding is 7. So we've got to decipher this quotient, and of course there's only 3 terms, so this now is squared, x term and constant, whereas it started off with cube, squared, x term, constant. It's gone down by 1 degree, hasn't it? Because you've divided everything by an x term. So what have you just proven? That the quotient is that's these two with the x term attached, and this is the remainder, and that was the divisor. So down here, these are screen clippings from Hayes and Harris publications here. We also had a problem before where we showed it was equal to that. So let's check that one out. If it's dividing by take 3, when you subtract it, that will be a plus 3. So that then when we do these processes, these become additions, making it easier. So 1 goes straight down, 1 by 3 is 3, neg 1 plus 3 is 2, multiplied by 3 is 6, adding them is 3, multiplying there is 9, adding them is 4. So the idea of reversing this sign here is in our, so that's divided by neg 3, but reversing it here is so that when we come to these lines of working with the coefficients, we're going to add them. We've incorporated the subtraction in a reversal of the sign of that constant. Okay, not a lot of maths in that, that's really just patterning and trying to follow the pattern of the coefficients as we go through the algorithm. All right, come down here and see, let's do 1 or 2 and have a look. So you're dividing a cubic by x plus 2. Don't forget 1x squared, negative 2, 1x cubed, negative 2x squared, and no x, and 3. Don't forget to put that in. Okay, and the divisor is x plus 2, so that goes negative 2. Put a 0 here, goes straight down to 1. 1 by negative 2 is negative 2. Adding them is negative 4. Times by negative 2 is 8. Adding them is 8, times by negative 2, negative 16, adding them is negative 3. So it's gone this many times, which is now a quadratic plus the remainder over the divisor. Or the other way around is to say the original function, well, they haven't written it, that's better, but they haven't written the other form, and that is that this function could be thought of as this many lots of the divisor and take 13, the remainder. So that's the other way of writing that relationship. All right, let's go down and do another one. Let's do a quartic, degree 4, divided by a linear. So first of all, 1x to the 4th or all, no x cubed term, so put a 0, take 1x squared, 2x and 3, and it's take 3, so this becomes positive 3, 0, and it goes to a 1. 1 by 3 is 3, added is 3. 3 by 3 is 9, added is 8. 8 by 3 is 24, added is 26. 26 by 3, 78, added 81. So quartic has gone down to a cubic, and these numbers here are the numbers down here for successive powers of the variable, and we've got 81 as a remainder. So you could also say that this polynomial is this many lots, the quotient many lots of the divisor. The divisor is x take 3 plus the remainder of 81. That's the other way of doing it. So you want to have a go at some of those. So it is optional, you're not required to do this in this particular course, but you might be interested in a quickie way of dividing by, remember, it's got to be x take k or x plus k. You can't have numbers in front here in this synthetic or contracted division. You're contracting it down into a smaller format. Okay, so there we have it. I want you to pause the presentation, have a go, and as usual, check the answers as you go. So let's have a look at the answers now. So there's 3b3 question. We've got most of question 1 there. Just try and get up there. Here, question 1. Pause it, have a look. All the coefficients have been detached, just working with the numbers there. And then question 2. So I hope you've enjoyed the start to the journey of polynomials. You can see it is quite a huge area, but keep your skills up, keep practicing, and I'll catch you in part 2 shortly. So for now, it's cheers from me.